Hello everyone. I'm going to start my presentation. Our paper is called Gait Monitor and Analyzer, a wearable sensor-based gait analysis system. So what is gait? Gait is simply a person's manner or style of walking. There is no single normal gait because normality depends on each person's characteristics. But what if the gait is abnormal for a person? So the gait cycle is divided into two phases. First, there's the stance phase, and then there's the swing phase. The stance is when the foot is on the ground, and the swing is when the foot is in the air. Gait disorders are what cause abnormal gaits, and they may reduce quality of life, be disabling, and they affect a very significant part of people above the age of 60, so a correct diagnosis must be made. Traditionally, diagnosis of gait disorders is made by observing the patient walking, writing textual reports, and without sensors. The limitations are that diagnosis could be subjective, there is difficulty picking up on details, and then tracking progress is complicated because you have to compare textual reports. The study of walking is called gait analysis, and it may be done with sensors. First, you estimate gait parameters with collected data. For instance, you estimate stride length. You find abnormalities, and then you match those abnormalities with disorders. A type of sensor that may be used to collect this data is the wearable sensors. Now, we chose the inertial measurement units. They've typically got compact dimensions, and they contain an accelerometer, a gyroscope, and sometimes magnetometer, and you typically place them on the patient's or subject's lower limbs. Our method for gait cycle detection and event identification is actually a mix of two methods based on sagittal angular rate peaks. Here we have the sagittal plane, and we have all these positive and negative peaks here. And first, we use Trojan-Yell-Waddell's method's trusted swing periods for detecting steps. Now, Trojan-Yell validated this method on both healthy and mobility-impaired subjects. And how it works is the positive peaks here correspond to swing phases. So you can define an interval, for instance, from here to here, where there had to be a swing phase. So you call it the trusted swing period. And if there was a swing phase, then there was a gait cycle. And then we use Sabatini et al.'s method to identify events based on these negative peaks here, the toe off and the heel strike, and then we use the timings to estimate temporal parameters. The method we chose for spatial parameter estimation is the optimally filtered direct and reverse integration, or OFDRI for short. It's a direct method because it's based on double integrating acceleration to obtain distance. And in theory, these methods are the best because they're based on physics. But then in practice, there's drift, which is accumulated error. How this method tries to tackle the accumulated error is by first filtering the acceleration signal with different cutoff frequencies to obtain the best candidate, so to say. And then you weight the integral of the best candidate signal with a reverse integral, which is actually the same signal but integrated inversely in time. And this is used by us and also employed by Trojan-Yell et al. For estimating spatial parameters. So now that we've presented the methods, we can present our proposed system, which is the Gait Monitor and Analyzer. It is a system for collecting representative gait data because the patient wears a prototype outside of the laboratory. They go about their daily lives. And the goal is to make it easier for physiotherapists to first diagnose gait disorders and then evaluate progress. And the system must be non-intrusive for patients since they wear it during their day. And it must be feasible for clinics, both in terms of monetary costs, as well as time and resources to train health professionals. The system is divided into three layers. First, there's the wearable motion sensing prototype layer. It consists of three wireless units, one on the shank of each leg, as well as one on the pelvis. This one is for estimating, it's for implementing Weinberg's method, although we didn't talk about it in our paper. And how this layer works is each unit, it will read data from its sensor and then transmit it through Bluetooth to a patient app, which is a mobile Android application. which forwards the data to the application server. It stores it in a database and a file storage. And then the physiotherapist also has an app that allows him to request the server to generate gait reports. And this is where gait parameter estimation occurs. And then the gait reports will contain mean values and standard deviations for each parameter, for instance. Talking about the units, each unit of the wearable prototype, it's got an IMU with the MPU 9250. It's got a board with the ESP32 microcontroller, as well as a battery in order to make it fully wireless. It's got compact dimensions and it's discrete. The positioning on the body is discrete, but the attachment is firm and also adjustable. You can fasten the units on the shank to a level you deem comfortable, as well as the one on the pelvis. And then in the client layer, we have the patient app. So the patient app is focused on simplicity because the patient probably never used the application. The goal is simply to start data collection and for the collection to be reliable. And then in the physiotherapist app, it's where the gait reports are presented under the form of mean values and standard deviations for each parameter. In this case, it's temporal parameters. We also have charts. For instance, for step time, we have the estimates of the parameter throughout the day, where we have highlighted the periods where it was considered unhealthy for the subject's characteristics. We performed an evaluation of the system. Point 1 was with a healthy subject walking on treadmill. Reference values were derived from speed, which was set on the treadmill, time elapsed, and the number of steps. And those values are here. And the estimates for temporal parameters, meaning cycle time, step time, and cadence. These parameters were estimated with accuracy and precision, and we can see that in the mean error and mean standard deviation of error for each parameter. We can see the values are indeed low for the temporal parameters. And for spatial parameters, meaning stride length and speed, they were both subestimated, and the results were slightly better for the right leg. Point 2 was with mobility impaired subjects. Now, we cannot derive reference values the same way because due to gait variability, the mean value of a parameter may not be equal to the value for each step, but we can still have a look at the estimates. And for subject A, a woman with a right foot and ankle fracture, the first thing that suggests there was indeed a problem with the right lower limbs was less steps being detected from the right leg. And this is due to the irregular signal that is shown here for the right leg compared to the left leg. And subject B is a man with dementia and balance problems. And it is curious that patients with dementia, they walk slowly, but then in relation to their motor and cognitive deficits, they actually walk too fast. And this could be reflected in a low speed, a short stride, but then a cadence that is normal, maybe even a bit high for the patient's characteristics. So to summarize, our method had more difficulty analyzing pathological gaits, but still several of them were reflected in the results, and we could differentiate them from a healthy gait. Point 3 is a cost analysis. The wearable prototype cost us around €100 to build. And by using the physiotherapist's smartphone and the patient's, no additional equipment is required. And the cloud component has variable costs, but for instance, for a clinic with 10 patients, the cost per patient would be €5.55. To summarize, technology like sensors can aid gait analysis in the context of physiotherapy, but there are still limitations that are being tackled by researchers. And we built the Gait Monitor and Analyzer system that estimates gait parameters through analysis of data from wearable sensors and generates gait reports. The obtained estimates for the healthy subject were satisfactory, and despite additional struggles when analyzing pathological gaits, it was possible to differentiate them from a healthy one. Of course, further validation and evaluation of the system need to be performed. So I now conclude my presentation.